We're here at the example table, and in this video we're going to be talking about quadratic equations. Let's start with just about the simplest case. Let's take, for example, x squared minus 6 equals 0. What makes this so simple is that the only occurrence of x is this x squared. There are no x to the first power terms. To solve this, we just move the 6 to the other side. We get x squared equals 6. We take the square root of both sides. We get x equals plus or minus the square root of 6. This kind of equation will always have a solution as long as this thing under the square root is not negative. Let's take a look at another example. Let's add one complication. Instead of just x squared, let's suppose that we have x minus 3 squared. Let's say minus 7 equals 0. We're going to go through basically the same process. We'll move the 7 to the other side, so we get x minus 3 squared equals 7. We take the square root of both sides. We get x minus 3 equals plus or minus the square root of 7. And now we'll also move this 3 to the other side, so we get x equals 3 plus or minus the square root of 7. So if we're given any equation of this form, or we can get an equation into this form, we know we can solve it through this basic process. We also know that we might not get a solution because this thing under the square root might be negative. But this is the form that we're looking for. Let's take a look at a slightly more complicated example. This is more complicated because not only do we have an x squared term, but we also have a linear term. We have this 2x here. Now at this point, it's good to recognize, or it's good to remember that something like x plus or minus a quantity a squared expands to x squared plus or minus whatever this sign is, plus or minus 2ax plus a squared. This is a really useful pattern to remember. We want to remember it here because we have something that looks like part of this. We have an x squared. We have something times x. We don't have this a squared term, but let's add it in. First, we have to figure out what a is. We want this term, this 2x, to match this. Well, to make it match this, we divide whatever this coefficient of x is by 2, and we'll get the a. In this case, the coefficient is itself 2, so our candidate for a is 1. So let's write x squared plus 2x plus 1. We want this plus 1 because if a is 1, then a squared is also 1. But we don't want to change this original expression, so if we add 1, we must subtract 1 as well. So let's set this now equal to 0. These two things are equivalent. They're equivalent, but this first part we can now write like this. This first part is x plus 1 squared, and then minus 1 equals 0. Now we have an equation of the form that we saw before. We know how to solve this. We write this as x plus 1 squared equals 1. Take the square root of both sides. We get x plus 1 equals plus or minus the square root of 1, which is itself 1. We'll move this 1 to the other side, and we get x equals negative 1 plus or minus 1. Let's make these 1's a little bit clearer. Let's look at a slightly more complicated example. Let's look at x squared plus 3x equals 0. Our approach is the same. This is just a little bit more complicated. Now, we'll take x squared plus 3x plus something. We want that a squared term. To find the a squared term, we have to figure out what a is. And remember, we took this coefficient and divided it by 2. So a is 3/2. A squared is 3/2 squared, which is 9/4. But again, we don't want to change the original expression, so if we add 9/4, we better subtract 9/4. And all of that equals 0. We'll factor this first part. This first part becomes x plus 3/2 squared minus 9/4 equals 0. And again, we know how to solve this. This basic process, I don't mean basic as in it's always easy. I mean this overall process is called completing the square. Right, our goal is to take something like this and get this square part from it. Let's take a look at one more example. Let's look at x squared plus 3x plus 1 equals 0. We didn't have this plus 1 there before. Our approach doesn't change, so don't let this confuse you. We still use this x squared plus 3x to figure out what a is. So we're going to get x squared plus 3x plus 9/4, right? Our a was 3/2. We're going to subtract 9/4, but now we just need to include this 1 again. So plus 1 equals 0. We factor this part into x plus 3/2 squared, and then the rest I'll leave to you. So the only complication that this 1 added is that we have to remember to include it in the end. It didn't change this 9/4, it didn't change this 3/2. Let's actually look at one more example before we generalize. Let's look at 5x squared plus 6x plus 1 equals 0. The complication here is that there's a coefficient of x squared. But since we're setting this equal to 0, it's particularly easy to divide everything by that leading coefficient. So we can transform this into x squared plus 6/5 x plus 1/5 equals 0. And we can approach this problem in the same way that we approached this one. I'll leave it to you to figure out what a should be, given that the coefficient of the linear term of x is 6/5. All of this is leading to a formula. So our goal is to solve ax squared plus bx plus c equals 0, and we are assuming that a is not equal to 0. In other words, this is a true quadratic equation. If a were 0, this x squared term wouldn't even be there. Well, let's go through the process that we just went through in general, right, for a general a, b, and c. As we talked about in the previous problem, or the previous example, the first thing we can do here is divide by a. So let's transform this into x squared plus b over a x plus c over a equals 0. Now, we want to use this part to complete the square. If b over a is our coefficient, we're going to divide by 2 to figure out what we want to put inside here that we're going to square. So we're going to have 1/2 b over a, which I'm going to write as b over 2a. Now, if we square this, we're also going to get a b squared over 4a squared term. That doesn't appear here, so that's the thing we need to subtract. So minus b squared over 4a squared plus c over a, right, our original constant term, equals 0. We know exactly the pattern now. Don't be intimidated by these letters. The process is exactly the same. We'll move the constant terms over to the other side to get x plus b over 2a squared equals, now this negative term becomes positive, so we get b squared over 4a squared, and then the plus c over a becomes minus c over a on this side. I want to do a little bit of rewriting. I want to get these two terms over a common denominator. So I'm going to multiply c over a by 4a. So then they'll both be over the denominator 4a squared. So we'll get b squared minus 4ac all over 4a squared. If we take the square root of both sides, we get x plus b over 2a equals the square root of this thing. Well, I'll take the square root of the top. We get plus or minus square root b squared minus 4ac. Take the square root of the bottom. We're left with just 2a. I don't need to worry about a plus or minus for both of these because I've already included a plus or minus up here. So we can write the square root of the denominator simply as 2a. If we move the b over 2a term to the other side, we get x equals negative b, and this is now all over 2a. So I'm going to write this all over 2a, negative b plus or minus the square root of b squared minus 4ac all over 2a. And that is how we can use completing the square to derive this formula for the solutions to a quadratic equation. This formula is called the quadratic formula.